So here in lecture 10.2, we're going to continue to talk about technology mapping, and we're actually going to show a very interesting model of the problem. The problem is going to be solved in a style called tree covering. And what's interesting is that it takes what feels like a very complicated Boolean algebra kind of a problem. I've got this giant net list of stuff that comes out of more or less the result of multi-level logic synthesis, and I've got a library of physical gates that I get to use, which gate goes where, to map the output of the synthesis to what I can actually start working with in layout. It turns out we're going to turn it into a very pure kind of a computer science problem. We're going to take the output of logic synthesis and require that it be a tree in a certain form. And we're going to take all of the gates in our standard cell technology library, and we're going to require that they be trees, tiny little trees in a data structures style, in a particular form. And we're going to turn it into a particular kind of a matching problem. It's going to turn into a very pretty, very stylized, surprisingly simple computer science matching problem. So let's go talk about how we can take the technology mapping problem and turn it into a covering problem with trees.
So we're going to talk about a very famous model of the technology mapping problem, maybe the most famous model, a model called tree covering. Your logic network to be mapped is put into a particular form. It's a tree of simple gates. We've already seen the simple gates part. We've seen the NAND gate, NOT gate version of the logic from the previous lecture. It's easiest to assume an absolutely minimal set of gate types, so we're actually just going to assume 2 input NANDs and NOT gates. Makes our lives easiest to describe the structure of the problem. And your library is also available, your technology library, your standard cell library of real gates is also represented in this same form, trees of simple gates. Each gate represented as NAND2s and NOTs. And now there's an associated cost, so we can say something about the quality of the overall mapping by adding the cost of all the gates that we use. What's interesting is that the method is surprisingly simple as an algorithm and even optimal, which is to say, once you have your problem mapped into this trees, gates, cost form, you actually get an exact and optimal answer. And I have to say that that's actually a pretty rare thing in the VLSI CAD business, to have any algorithm that actually gets a best possible example in a surprisingly simple form in a surprisingly efficient algorithm. So the original reference is by my friend Kurt Koitzer, who's now a faculty member at the University of California at Berkeley. I believe that he was at AT&T Bell Labs when he invented this. So the paper's called DAGON, Technology Binding and Local Optimization by DAG Matching. It's in the Design Automation Conference in 1987. Definitely worth a read if you can find it. So what are we starting with? We're starting with your uncommitted logic that we want to do tech mapping on, and we're going to assume that what came out of multi-level logic synthesis was a network of nodes, each of which was a sum of product form, and then we replaced all the sum of products form with a network of nodes that are only NANDs and only NOTs, and we connected everything up. And this has a name, it's called the subject tree. And we're going to restrict things to 2 input NAND gates and inverters. It makes everything simple. You can take any piece of logic you want, even a complicated 2-level sum of products form with a big NAND gate, a big OR gate, if you will, and you can turn that into NAND gates. It's just, a little sort of De Morgan stuff. I've got a nice little example here on the right. It's got 4 inputs, A, B, C, D on the bottom, and an output called capital Z on the top. And there are a bunch of internal wires, and they've all got names. So input A goes into an inverter, makes an output called P. Inputs B and C go into a NAND gate, makes an output called Q. P and Q go into a NAND gate, makes an output called R. Input D goes into an inverter, makes an output called S. R and S go into a NAND gate, makes an output called T. T goes into an inverter, makes an output called Z. That's my subject tree. That's the little tiny example we're going to play with to see, what mapping is actually all about. And interestingly, your technology library also is an important part of this problem. And the first problem we have is that the technology library is not represented in the NAND and NOT form. Right, so typically the technology library is just a set of useful small logic functions. So let me give you an example of a set of useful small logic functions. This is an example, by the way, that I took from chapter 10 in Nani DiMichele's book. So this is a nice example. What's in my technology library? An inverter, which we're just calling a NOT gate. A NAND2, which is a NAND gate with 2 inputs. An AND2, which is an AND gate with two inputs. A NOR 2, which is a NOR gate with two inputs, and OR 2, which is an OR gate with two inputs. Something complicated, an AOI 2-1. So this is a layer of AND gates, and then an OR gate connecting those products, and then an inverter at the output. And how many inputs are there, or how many OR gates are there? Sorry, how many AND gates are there? Answer 2. How many inputs do they have? Well, the first one has 2 inputs, and so I'm just going to draw it. That's the one with 2 inputs. How many inputs does the next one have? Oh, it has only 1 input. That's why we draw it as a wire, but I'm going to draw this in a little sort of a kind of a dotted line way here. You know, there's really an AND gate, if you will. There's really a vestigial AND gate, a phantom AND gate there. It's just got 1 input. What's a 1 input AND gate? Well, that's actually just a wire. So this is an AOI 2-1. This is perhaps the first time you've seen a primitive logic element that is asymmetric, right? Not every input is the same. Here is the symmetric version, a slightly bigger version, AOI 2-2. Again, a layer of AND gates. A single OR gate connecting those AND gates, and then an inverter at the output. How many AND gates are there? There are 2. How many inputs do they each have? Well, the first one has 2, and the second one has 2, so that's why this is AOI 2-2 as opposed to the gate on the left, which is AOI 2-1. Okay. Nice, simple, kind of, it's easy to explain why one would want to be able to use these gates in our logic, but as I mentioned when we started this slide, the new problem is that it's not in the required form. Remember, the only thing I get to play with are things made out of 2-input NAND gates and inverters. So I have to take this thing and I have to transform it into the appropriate form. Now, that turns out not to be too hard. So I've got the library again drawn as a little kind of highlighted box in the top right-hand corner of the slide. A NOT gate, a NAND 2, an AND 2, a NOR 2, and OR 2, AOI 2-1, and AOI 2-2. All right, so 1, 2, 3, 4, 5, 6, 7 gates. 1, 2, 3, 4, 5 of them, I would say simple gates, 2 of them complex gates. I need to transform this so the only thing I see are 2-input NANDs and inverters. That's pretty easy. So the inverter, well, heck, that's just an inverter. Life is easy. The NAND 2 gate is just a NAND gate. The AND 2 gate is just an inverter with, a NAND gate with an inverter at the output to get rid of the complement. I'll admit that the NOR 2 looks kind of ugly. You know, the NOR 2 is 2 inverters going into a NAND gate whose output goes through an inverter, right? This is just the De Morgan law that says, you know, X plus Y with a bar over it is X bar and Y bar. So there's 2 input inverters giving you X bar and Y bar. But the problem is that it's a NAND gate, so I've got to get rid of the bubble. So that's why there's another inverter there. The OR gate is simply the NOR gate without the output inverter. So it's 2 inverters leading to an NAND gate. The nice thing about the AOI structures is that they really are sum of products forms. They're supposed to be a layer of AND gates, an OR gate, and then an inverter. You know that a 2-level form and or structure, you can just replace the ANDs with a NAND and the OR with a NAND, and it all just works. The only thing you have to be a little careful of here is that it is an inverting logic, and so it has to be the complement of the sum of products sort of a form. So you get an inverter at the output, and if you're careful with the De Morgan law, the wire, right, which was, as I said, kind of a 1-input AND gate, when you turn that into a NAND gate, you get a 1-input NAND gate. A 1-input NAND gate is an inverter, so you just got to be a little careful on that one. So this is a NAND gate with 2 inputs and NOT gate with 1 input. Those 2 outputs go to the NAND gate. The NAND gate goes through one more inverter to get the polarity right, and you get an AOI 2-1. And AOI 2-2 looks exactly like that, except the wire with the inverter on it is replaced with a NAND gate. So this is a nice symmetric structure. You have 2 2-input NAND gates going into a single 2-input NAND gate, which goes through one inverter to get the polarity right. And here we are. I have accomplished what I wanted. My technology library is represented in exactly the same form as the output I get from multi-level logic synthesis. In this form, each library element is called a target tree. So recall, after I took the output of multi-level logic synthesis and turned it into NANDs and NOTs, I called it the subject tree. After I took every one of the elementary library gates, and even the complex gates in my technology library, and turned them into nands and nots, it's now called, each of them is called a target tree. So what's the essential idea of tree covering? And this sounds a little strange, but the idea of tree covering is I want to avoid doing any Boolean algebra. Even though we're actually kind of pretty good at that at this point, I don't want to do this with any Boolean algebra. I want to do this by just essentially pattern matching, like matching a string. A capital B matches a capital B, but a capital B doesn't match a lowercase x. The technology library, which I'm again showing at the top left, a not, a NAND2, AND2, NOR2, OR2, AOI21, AOI22, each expressed specifically in NAND2 and NOT gates. And on the right, I've got my little pattern, my little subject, right, the Z tree. And so this has A, B, C, and D as inputs, Z as outputs, internal nodes P, Q, R, S, T. It's got 3 NANDs and 3 inverters. What you will notice is that every one of the gates in my technology library is nothing but 2 input NANDs and inverters. And the thing that I am matching, right, the thing that I am mapping onto these gates is itself just 2 input NANDs and inverters. I can do this mapping process by just making sure that I pick things from the technology library where the gates match exactly. No Boolean algebra at all. So I am allowed to match things like NAND gates to NAND gates, and I'm allowed to match things like inverters to inverters, and that's it. So look, here's a concrete example. Let's select the AOI21. So it's got an inverter on the top, and then a NAND gate, and then the inputs to the NAND gate are 1 NAND gate and 1 inverter. And if we look over at the subject tree, what we can see, and I've got it colored in a kind of a highlighted way, is that the top of the Z tree looks exactly like an AOI21, right? It starts with an inverter on the top, so I'm going to put a little check mark by the inverter. And then when I look below it, the thing going into the inverter is a NAND gate, and that looks like it matches. And then when I look to the left, in this case, I see a NAND gate going into the NAND gate, and oh yeah, that's what AOI21 has. And then when I look to the right, I see an inverter, and it's like, oh yeah, that's exactly the same. I can actually make the output of this Z function by putting an AOI21 as the output of this little logic network. This very simple-minded matching process has a name. It's called structural mapping. Find where in the subject graph the library pattern matches everywhere. And there's a very simple set of rules. NAND matches NAND, NOT matches NOT, and so on. All right, so that's the essential idea in tree covering. We are going to take elements from the technology library and we're going to put them on top of the subject tree and make sure everything lines up in some fairly simple way with some quite simple rules. And the only matching that I have to do is like gates have to match. So just to sort of summarize there, the general tree cover representation is a structural technology mapping. There is no Boolean algebra anywhere. We just match the gates and the wires in a simple pattern matching kind of way, and the result is a surprisingly simple covering algorithm for the cost optimal cover. But first, I want to simplify the way we draw these because there's still just too much going on in these diagrams, and I want to sort of emphasize the fact that this really is a very simple kind of a pattern matching kind of a process. And so I'm going to show you how we're going to represent the trees for covering. On the left, again, I'm showing my little Z subject tree, inputs A, B, C, D, output Z. There are 3 NAND gates here, 3 inverters here, internal nodes P, Q, R, S, T, just as before. Look, there's only 3 kinds of things you can match looking at this tree. And so we're just going to draw it in a really simple-minded way to sort of remind ourselves that there's only 3 things going on here. The first is that there are NAND gates. So instead of drawing a NAND gate, I'm going to draw a circle, and I'm not going to fill it in. So I'm just going to draw a white circle. Every place you see a white circle from now on, that's a 2-input NAND gate. And the inverters, I'm going to draw a black circle. Okay, and I'm just, this is sort of arbitrary. The Nani DiMichele book has a different sort of notation for doing this. I'm trying to be even simpler than the way he's doing it. I think this is merited. So an inverter is a black circle and NAND gate's a white circle. And then there's also something that's not so obvious you need. There are inputs, right? And the inputs are square boxes. Okay? So a NAND gate is a white circle, a NOT gate is a black circle, and input is a square. So if I take the Z subject tree on the left side of this diagram, and I draw it again on the right, this is what it looks like. So there are 4 inputs, A, B, C, and D. Those are now square boxes because those are inputs. We actually have to be careful that we represent those things. We have to match those things too carefully. The A input goes into a black circle because A goes into an inverter that makes the output P. B and C go into a white circle because B and C go into a NAND gate. Okay, the P wire output from the inverter, the Q wire output from the NAND gate go into a white circle because P and Q go into a NAND gate that makes output R. And so that's a white circle. Input D goes into an inverter. That goes into a black circle. That makes an S. R and S go into a white circle because that's a NAND gate. That makes T. T goes into a black circle. That makes Z. So this is just one-to-one exactly the diagram on the left-hand side here, but it looks very simple, right? Just the white circles, black circles, and boxes with letters on them. Now, you have to actually make the technology library in exactly the same style in order to execute this algorithm. And so I'm showing you a picture of the tech library as gates, again, simple NAND and NOT gates. So there's a NOT, a NAND2, an AND2, a NOR2, and OR2, AOI21, AOI22, 1, 2, 3, 4, 5, 6, 7 gates in my technology library. Every one of these things has to be represented in the same stylized graph form. So there's the NOT gate. What does a NOT gate look like? It's a square representing an input going into a black circle. There is a NAND2 and an AND2. The NAND2 is just a white circle with 2 children left, right that are inputs. The AND is a black circle because it's an inverter at the output of a NAND, which is a white circle with two boxes that make the inputs. NOR2 and OR2 are a little more complicated. Remember, NOR2 was a NAND gate with inputs at the inputs and the outputs, so it's a white circle. Output goes to a black circle. Inputs come from black circles, 2 input boxes. The OR looks just like it, but omit the output black circle. AOI21, a black circle at the top because it's an inverter. That's fed by a NAND gate, a white circle. The inputs to the white circle, 1 white circle with 2 inputs, 1 black circle with 1 input. The NAND and the NOT respectively. AOI22, black circle at the top, fed by a white circle fed by 2 white circles, each white circle fed by 4 square boxes. All right, so this looks much simpler than what we started with. There is no Boolean algebra happening here at all. This is a very simple structural mapping problem. And so, I'm showing you now the sort of the structural mapping problem in its sort of precise form. I'm showing you the technology library at the top of this diagram, NOT, NAND2, AND2, NOR2, OR2, AOI21, AOI22, and each one of them is the little set of black and white circles and boxes from the previous slide. And at the right-hand side, I'm showing you the little Z circuit again, A, B, C, D inputs, Z as output, internal nodes P, Q, R, S, T, 3 white circles, 3 black circles. And structural mapping says I have to find where I can fit the library gates, which are black circles, white circles, and square boxes, on top of the Z circuit and match with a simple set of structural matching rules. What are the rules? The rules are mostly really easy and mostly really obvious. A white circle matches a white circle. You're allowed to put a NAND gate only where there's a NAND gate. So a white circle matches a white circle. A black circle matches a black circle. You're allowed to put a NOT gate only where there's a NOT gate. And this is the one that's maybe a little bit complicated. We need to talk about this just a little bit. A square box which represents the input to one of the library elements or the input to the overall subject tree, the thing that popped out of multi-level synthesis, that matches anything. the way that works is the way that it matches anything. That's how it's possible for the output of one gate to connect to the input of another gate. And we're going to talk about this with a little example here. So let's just start by doing a sort of a complicated thing. So I've got the technology library again shown at the top, not NAND, and NOR, or AOI 21, AOI 22. And I've got my little Z tree on the right, 4 inputs A, B, C, D, 3 black circles, 3 white circles, Z at the top. The AND or invert 2-1, as we already said in a previous slide, matches at Z, right? It's got, a black circle at the top, and then a white circle one level down, and then one white circle and one black circle as children and inputs, right? The AOI 2-1 matches at Z because of two things, right? So the first reason it matches is that all of the internal nodes match exactly. And so I'm going to highlight the AOI 2-1 for you here. And then I'm going to highlight how the AOI 2-1 matches, right? So at the top, there's a black circle, and the black circles match. There's one child of the black circle, and it's a white circle. Those things match. There are two children of the white circle, a white one on the left and a black one on the right. Turns out that matches exactly as well. White one on the left, black one on the right. I'm just checking the little boxes in the AOI 2-1 picture. All right, those are all the internal nodes. And then I'm going to put a star by this. It's in red over here. And the inputs match anything. And so what that means is, just to be very clear, the leftmost input of the NAND gate circle, the white circle of the AOI 2-1, matches P, which is to say it matches the black circle that makes P the internal wire. Now that's an inverter. Inputs match anything, right? So that white box matches the black circle that makes P. The next input to the NAND gate, the right input to the NAND gate that's at the bottom of the AOI 2-1 matches Q. That matches a NAND gate, right? So just to be clear, the left box matches the inverter, the right box matches the NAND gate at Q, because inputs match anything. And going forward, the third white box at the bottom of the AOI 2-1, the input to the inverter in the AOI 2-1, matches the D input. It matches a box, another box, right? All of this works. All of this is required in order to have the semantics of the overall matching of how gates cover the tree work out okay. All right, so internal nodes must match exactly. We saw that in a kind of a simple way, and inputs match anything. Now there's one kind of a careful thing you got to just be careful about. We haven't shown this in any of our examples so far, but the symmetries matter. So on the left of this diagram here, I'm showing you an AOI 2-2. It has an output inverter, a NAND gate connected to that inverter, and then the inputs to that NAND gate are another 2 NAND gates. It has a symmetric tree. A black circle fed by a white circle fed by 2 more white circles fed by 4 white boxes. I don't care which way you sort of match. There's nothing asymmetric about this one. That's not true if you look at something like the AOI 2-1, right? I mean, I have drawn the AOI 2-1 as a NOT gate being connected to a NAND gate being connected on the left to a NAND gate on the right to an inverter, but there's no reason on earth that I couldn't flip that, and I've got a little red arrow here that flips it. Now the inverter is on the left and the NAND gate is on the right. And I'm just showing you the black and white pattern trees. The one way of doing it has a white circle on the left and a black circle on the right. The other one has a black circle on the left and a white circle on the right. This is not a symmetric pattern. When you're matching, you actually have to rotate it and see whether either orientation will match in your subject tree. So how does one actually do a complete tree cover? Surprisingly, there's 2 simple rules. Every node in the subject tree is covered by some library tree, and the output of every library gate overlaps the input of the next library pattern. That's basically it. Right, so everybody is connected to something, or everybody uses some gate, right? And wherever the output of a gate is mapped onto the subject tree, well, then that has to be overlapped by the input of some other gate, and you just sort of go from the bottom to the top. So let's just say that I'm only going to use NAND 2s and NOT gates to map this tree. What's a complete mapping? All right, so here's a complete mapping. So on the right-hand side, again, the Z subject tree, A, B, C, D, white box inputs at the bottom, Z at the top, 3 white circles, 3 black circles, P, Q, R, S, T nodes, intermediate, the outputs of gates. Let us talk about the matching. The first thing I can do is I can put a NOT gate at node P. And so what that means is that the output of the NOT gate is connected to the P wire. The black circle matches the black circle, and the input to the NOT gate matches the A input to the overall Z circuit. And similarly, I can put a NAND 2 gate at the Q node, which means the output of the NAND gate matches the white circle that generates Q, and the inputs to the NAND match the B and C inputs. And here's where that output-input thing becomes critical. I can put a NAND gate, a NAND 2 gate at the R node. And so what that means, the white circle matches the R node, but the inputs match on the left, the P node, which is a black circle, and on the right, the Q node, which is a white circle. And what we're already noticing is, hey, I've already mapped something else there. Yes, you have. The output of the NOT gate at P drives the input to the NAND gate also at P. The output of the NAND gate at Q drives the input to the NAND gate also at Q. That's how that works. So I could also put a NOT gate at node S. Black circle matches black circle, input matches input. I could put a NAND gate at node T. Again, you look and you say, hey, node R is covered twice. Node S is covered twice. Yes, of course, it has to be. The output of the NAND 2 at R is the input of the NAND 2 at T. The output of the NOT at S is the input to the NAND 2 at T. I could put a NOT gate at node Z. And again, the input to the NOT gate matches node T, but that's the output of the NAND gate. This is a legitimate mapping. Everything is covered, and the output of one gate pattern connects to the input of the next gate pattern, and everything is covered. This is a real gate network. You could actually draw this as logic, real logic. It's not a very interesting mapping, I will admit, but it's a structurally correct mapping. So this is one correct tree cover with 3 NAND 2s and 3 NOT gates. So, usually there are many, many different legal covers. Which one do you choose? The answer, and this is what we're going to spend the rest of this lecture on, is the one with minimum cost, because every gate has a cost associated with it. So now let's assume that the library has a little more interesting stuff in it. It has a NAND 2, a NOT, and an AOI 2-1, which I'm drawing. And again, the Z tree on the right, ABCD inputs, 3 black circles, 3 white circles, Z at the top, PQ, RST, internal nodes. I can do that same exercise. I could put a NOT gate at node P. That matches correctly. I could put a NAND gate at node Q. That matches correctly. Its inputs are on B and C. I could put an AOI 2-1 at node Z, and it maps everything else, because the AOI 2-1 is a great big complex gate pattern. So the AOI 2-1 covers node Z, node T, node R, node S, and its inputs, okay? Its inputs map to the output of node P, the output of node Q, and the D input. And so this is another legal cover, another legal mapping of this design, a different tree cover, one NAND gate, one NOT gate, and one AOI 2-1. Oh, which one do I pick? Answer, I pick the one with the minimum cost. I have a cost associated with every gate. I add it up. I pick that one. How do I compute that? Answer, a beautiful, a lovely, a really elegant, delightful algorithm, which is, no surprise to anybody in this class at this point, a recursive algorithm. So let's go talk about how that works next.